Alright guys, how are we doing? You guys ready? I can wait a couple minutes. You good? Alright, hopefully the band won't be too loud tonight. They're farther away, but it seems louder. It must be just the way the hall works. So, alright, so remind me, what did we talk about last week? Thermodynamics. Somebody just got tutored. Very nice. So what's thermodynamics all about, sir? How heat affects stuff? Okay. So what is heat? That was the perfect lead in. What's heat? The flow of energy, correct. Is heat energy itself? Yeah, it's moving energy, right? Is temperature energy? No. What is temperature? So what is that? Measurement, right? So it's just a signpost. Stuff flows from what to what? Hot to cold, right? All right, very, very good. All right, we also talked last week about thermal conductivity. Dustin, what's thermal conductivity? Okay, in what? How conductive heat is in what? In a material, right. So that is just like a couple weeks ago, we talked about resistivity, which is the ability of a material to resist or conduct electrical flow, electrical current, right? And thermal conductivity is the same concept, just how well it conducts heat. So you guys remember we talked about conduction, right, where a molecule will be going like this, and then a molecule will be going like this, a lot faster, bump into it, now they're going the same speed, right? So that's how a hot molecule, or a hot atom, or a hot molecule, or whatever in a material can continue to conduct all the way down the line. Yes? Oh, no question? Okay, sorry. All right, so tonight we're going to talk about reliability engineering, and this is actually my favorite one to talk about. I really enjoy this one. Just a reminder, there is no lab tonight, so this one will be shorter than normal. So again, feel free to ask questions as we go through. All right, so before we start, I want to do a quick probability refresher. Right, I know all you guys know this like the back of your hand probably, but let's get on the same page. So, probability is the number of desired outcomes divided by the number of possible equally likely outcomes. Okay, so I use the die up there. You can see it, right? If I were to roll a die, what is the probability of getting a 6 on one roll of the die? 1 over 6, right? Because there's each side of the die can equally be rolled, and there's one chance, right? And then what would be the probability of getting a 1 or a 6? It would be 2 divided by 6, or 1 over 3, right? So reminder, for probability, it is, what's 0% in probability terms? What's that? Impossible, no chance of happening. And what does a value of 100% mean? Absolutely certain, right? But we use percentages, or do we use 0. For probability, we actually use like a 0.1 to represent 10%, or a 0.9 to represent 9%, or 90%, sorry. Okay? So you guys have got that down. That's all second nature for you guys, right? So, just a reminder, here's not example 1, but if events A and B are independent, which means that they have the same chance of occurring regardless of what each other is. For example, like a coin, right? If I were to take a coin and flip it twice in a row, the second flip, would the second flip matter at all what the first flip was? The answer is no, right? So I could flip a coin twice, and I could get 2 heads. I could get a heads and a tail. I could get a tail and a heads, or I could get a tail and a tail, right? So the probability of these, let's go back. So the probability of A and B happening, how do I calculate that? Possibility of A times possibility of B. Probability A times probability B. Very good. So in that case, right, let's say I wanted to flip a coin twice and I wanted to get heads twice. How would I calculate that? 1/2 times 1/2. Very good. For a total of what? 1/4, or 0.25. Very good. All right, now let's say I want to flip a coin twice and get heads on one of them. How would I calculate that? Malika, you're on fire. Keep it going. Probability to get heads? Mm-hmm. Okay, so in the case that we're looking at A or B, what we do is we actually add them together and then subtract. But you're actually on the right track. So you're actually about 2 slides ahead, because I find it easier in cases like this to do exactly what you're saying, which is actually calculate the success of failure and then 1 minus it, right? That's actually typically the easier way to do it. So you're actually ahead. Very nicely done. All right, so in this example, if I roll 2 dice, what are the probability that both dice will roll a 1? It's 1 over 6 times 1 over 6, which is 1 over 36. Relatively low probability. In example 2, if we roll 2 dice, what are the probability that either of the dice will roll a 1? So we can use that formula there, probability of A plus probability of B minus the probability of the ands. So it's 1 over 6 plus 1 over 6 minus 1 over 36, and we get 11/36. But if we want to do it the way Malaika did, which is actually my preferred method as well, we can do 1 minus the probability of failure, right, which is 1 minus 5 over 6 times 5 over 6, which is 1 minus 25 over 36, which gets us the exact same answer, very well done, at 11 over 36, and the answer is the same. And this is the preferred method. So is anybody unclear on any of the probability stuff, right? This is super simple. You guys are probably doing this like maybe even in elementary school, like 5th, 6th grade probably, right? All right, so we're going to use that for our basis of reliability engineering. So does anybody know what reliability engineering is, or have any clue what reliability engineering is? Yes, sir. Okay, sure. So what do I actually mean by that? What does that actually mean, right? So you're correct. It's the engineering of reliability. But what does that mean? Okay, very good. Yes, that's our main objective. Yes. So I want you guys all have your cell phones, right? All right, let's consider your phone, right? My phone looks probably way older than yours does, right? But what does your phone, what parts are in your phone? What are the functional parts of your phone? Let's just start naming a few. Yeah, there's a lot, right? But what are the major parts of your phone? What's that? Your screen. Very good. The power button. What else? The battery. Yeah, that's an important one. What else? The home button. Okay. Yeah, especially on an Apple. That's all you have, right? On iPhones, you don't anymore? All right. Fair enough. All right. What else? What other components? Thomas, what else? The board inside, the brain, the computer, the CPU, whatever you want to call it, right? Is that what you're saying? Yeah. Okay. Anything else? Camera. Perfect. Screen. We got screen. What else? What's that? The operating system. Okay. So the software. All right. So I went ahead and I listed some as well. So I have the screen, the battery, the keyboard, the input, right? So the touch part of your screen. I have the chipset, the microphone, the speakers, the modem, and the antenna. So now let me ask you this. In order for your phone to work, what actually needs to be working? So let's actually put it in a more simple context, right? So Daphne, you need to call your boyfriend, right? How are you going to do that? What do you need to do from start to finish to call your friend, whatever? All right, so you pick up your phone, you unlock it, you tap in the numbers to unlock it, or you just unlock it, swipe it. Okay. Type in the phone number, or maybe you say Siri, call Jim, whatever, and then you talk, right? So let's think about that functionally. What needs to be working for you to unlock your phone? Battery, because your phone needs to be on. What else? The screen, perfect. And not just the screen. The screen doesn't just need to be showing, but what else does it have to be doing? It has to read your touch, right? So now we have 2 things just in the screen working. What else has to be working? You need the antenna. Yes, very good. The microphone, very good. All right, so let's say your success criteria now is make a phone call. So we just, I think it was 5, it was maybe even 6 things, right? So we have 6 things on our phone now that have to be working in order for you to meet success criteria. Okay? What happens if any one of those doesn't work? You cannot make your phone call. Now, you may be able to still, if say microphone's down, you may be able to surf the internet, If your camera is not working, you might not be able to Instagram, but maybe you can still make a phone call, whatever, right? But functionally, in order for your phone to turn on, what has to be working? The power button and the battery, right? And probably also the software, the chipset. Okay? So what we're starting to think about, or what I'm trying to get you guys to think about here, is functionally, in order to accomplish a task, we have to have multiple things that happen, right? And the phone's very straightforward. So now if we go to the next step, is product reliability. Okay? As engineers, or actually as consumers, we actually naturally expect the things that we buy to work, right? You don't want to go to the store, buy an iPhone, and have it not work, right? It's probably going to make you angry, especially if you bought the new iPhone that's like, what, $800 or whatever it is, right? Right. We expect our electricity to stay on. We don't even really think about it. Who gets annoyed when their internet goes out at home? I know I do. It drives me crazy, right? We expect that as a basic utility to stay on. We expect things we buy to work for long after we buy them. We don't expect our iPhone to just work for a day and a half. We expect it to work for 2 or 4 years, right? So if products or services don't perform the way we expect them to, as engineers and as company owners, or as people part of a corporation who are making that product, if our stuff's not working, people aren't going to buy our stuff, right? Let's say word gets out that the new iPhone 23 is not, it doesn't work very well, right? As soon as it gets out in the news that the iPhone 23 is not good, you're going to have CNET's going to be posting about it, the reviews are going to be bad, and they're going to see less sales, right? That's not going to be good for the bottom line of the company. Might be layoffs. They might have to go back and figure out what happened. And again, if 1 out of every 10 iPhones sold broke, right, by the same logic, people aren't going to be buying as many iPhones, right? Or they're going to have to go back and fix those iPhones, which is going to cost some additional money. You're going to see it on the bottom line. So reliable engineering is thus actually, reliability engineering is engineering in its most practical form. Will our design work? Will what we're building do what it's supposed to do? How long will it do it? And how many of our parts the company produces will perform adequately? So the ultimate goal of reliability engineering is to evaluate the ability of a product or a process to perform its intended function for the given period of time that we determine as a success criteria, right? So again, if you just open your iPhone and it turns on the first time, that might be your success criteria for that, but you don't want your iPhone to just turn on once, you want it to last for a period of time. So we also care about how long, the duration, the failure rate of things, okay? So what is reliability? We say that something has failed, and that's a generic term. We say something has failed if it can no longer do what we wanted it to do, right? So in the case of your phone, right, you couldn't call your friend, which means that your phone has failed for calling your friend, right? Now again, if you're trying to go on Instagram or something, maybe it hasn't failed for that, but your phone is not doing what it's supposed to, your phone has failed. The concept of failure is an either or scenario. You don't kind of fail. You either are working or you're not, right? It's very binary. It's a 1 or it's a 0. It's a yes or a no. Make sense? And the likelihood of that failure is characterized by the concept of reliability. Reliability is the probability, and this is why we were talking about earlier, reliability is a probability that an item will do what it's supposed to do for the period that we want it to do it for. So in simple terms, reliability is a likelihood that a device will operate without failure for the duration that we need it to. We can calculate reliability this way. So say we test N devices, X devices, whatever you want to use as your variable. We test them for a time t that we define, right? So in the case of the iPhone, maybe we want to test it for 2 years. Our phone's still on a 2-year recycle rate. Is that a thing anymore? It used to be back when I was like your age, you'd buy a phone for a 2-year plan because that was about how long they expected phones to last for. They don't really do that anymore. Yeah, phones are probably more reliable than that. So, all right, fair enough. But so at the end of testing, so let's say we're going to test our phone for 1 hour. Just throw it out there, right? If I test 100 phones for 1 hour in however we're testing it for, and 99 of those survive, we have 99 survivals and how many fails? 1. So we plug it into our reliability formula. So R in this case of 1, right, of t, R of 1 hour, in this case would equal 99 divided by 99 plus 1, right, the total, and we're going to get our probability of every probability of that working for that period, right? So of every 100 iPhones we sell, we expect 99 of them to work for an hour. Now obviously it needs to be significantly better than that, right? But you get the concept, okay? And remember, we express this as a probability, so it's a number between 0 and 1. The reason we do it between 0 and 1 and not as a percent is because we're going to be multiplying these things together, right? Just as we saw in probability, right? This chance of your microphone working and your screen working and your touch, and right, you guys get the point. Okay? So obviously a reliability close to 1 indicates that we're doing well, right? We want to be close to 1 as possible. And reliability of 0 means that we're not doing our job very well. Right. So we already talked about failure. Now we can do something very similar for failure. Because success and failure are mutually exclusive, we can essentially calculate it by this. The failure rate over time t is the number that failed over the total tested, right? It's just 1 minus, right? You guys get that idea, right? So the probability of the reliability over time t plus the failure at time t is 1 minus, or equals 1. So failure is 1 minus. And that's an important concept. Probability of failure is 1 minus reliability, right? I've said that like 9 times. I'm going to keep saying it because it's very important. Reliability is 1 minus failure. And it's important because it makes our calculations incredibly easy, right? And that's exactly why Malika went to exactly where she did at the very beginning, because it makes it way easier to calculate. All right, so if you guys could please go to page 52 in your handbook. Okay, so 20 widgets were tested for a period of 200 hours. After 100 hours, 2 units had failed, and at the end of testing, a total of 5 units had failed. What is reliability 100, and what is reliability 200? And what is the probability of failure for the entire testing period? Formula is number of successes and or number of failures divided by the total being tested for that period. In other words, it's your probability, right? Number of successes divided by total opportunities. All right, Rahul, what did you get for the first one, reliability 100? 10%, okay, you got 0.10. Okay, is that what everybody else got? So is that the probability of success, or is that the probability of failure? Yeah, that's the probability of failure. So what's my probability of success? 90, 0.9. Is that what everybody else got? Yes. All right, how about reliability of 200 rule? 0.75% is reliability 200. Is that what everybody else got? All right, so very simply, we put it into our formula. We get 0.9, 0.75, and then what is the probability of failure for the entire testing period, Lynn? Do it real quick in your head. So failure is 1 minus reliability. What'd you get, Jairam? Didn't do that one? Chandler, do you have this one? Okay. Did you get it, Daphne? 65%? All right, so to find the probability of failure of the testing period, we can either calculate it from the formula or by using 1 minus. So I got 0.25. Because remember, it's 1 minus, so the entire testing period, right, entire testing period is 200 hours. At the end of 200 hours, 5 units had failed. So it's just 1 minus our 200, which is 0.75, to give us a 0.25. All right. So again, R100 is 0.9, R200 is 0.75, and the failure at 200 is 0.25. All right, so that's simple enough, okay? Anybody in a lab can do that. That's not really engineering. It does help an engineer decide whether their product is good or not, but that's not what you guys are going to be engineering. What you guys are going to be looking at is the system as a whole, okay? So a system is a set of components arranged to do something. Again, I'm going to go back to the phone example, right? Your phone is a bunch of parts that work as a system together to do something. The performance of that entire system depends directly on the performance of the individual components that make up the system. Again, right? Keep pounding on the phone. The reliability of the system the reliability of the total system can be estimated by looking at the reliability of each individual component. Okay, so let's say that your battery fails half the time. Do we expect your phone to fail half the time? The answer is at least half the time, because what if your screen fails quarter of the time? Right, now it's 0.5 times 0.25, right? So each individual component's failure rate starts to matter, and they can start to add together. So in this text, we're going to define the reliability of the system. You'll just see it as R sub S, okay, reliability system, and the reliability of an individual component as Ri. Or we may actually do subnode of like reliability of screen or something like that, right? But I being your iterative variable, right, like in your sum, okay? So, system reliability. Before an analysis is performed, we have to identify the logical contributions of each component. What do I mean? What do you think I mean by that, Ryan? What each thing does? Yeah, so what I'm trying to say is we have to evaluate the effect that that failure would have on the system. Okay, so think about it. What would the failure of a certain part do to the system? Would it make it fail? Right, so we already talked about that again with the phone. If the camera fails, you can still use your phone. Right, so if the camera fails, you don't necessarily have a failure from making a phone call standpoint. Make sense? So in that case, if the camera failed, it would not make your phone fail, so it would have very little impact on the reliability of your phone. Now obviously from a real life standpoint, you don't want your camera to die. You're going to go get a new phone, so actually your success criteria is probably that it needs to work. But you need to evaluate how each component fits in. And then does another component provide a similar function, allowing the system to keep working, right? So let's say in the case of the phone, that the microphone or the speaker that you would normally hold right here doesn't work. But you can turn your phone on speaker version and you could still talk like this. Your phone could technically still work then, right? You just have to walk around doing this all the time instead of listening like this, right? So your phone could still work. So then in that case you have two things that can essentially serve the same purpose. Right, so you guys are already quite familiar with the concept of series and parallel from circuits, which we already talked about. So from a reliability standpoint, components are either modeled as being in series or being in parallel. Madison, what do you think it would mean for something to be in series with each other? Yeah, that's correct from a circuit standpoint, but it's slightly different in the reliability world in that your phone, right, the battery may not actually be directly connected to the microphone of the phone. But if they both go out, the phone still fails, right? So we would model that, and this ties back into what I was asking you about, right? About you have to evaluate the use of each component. So again, the battery may not be directly tied to the microphone, but if you lose both of them, or sorry, if you lose either one of them, your phone still fails. So if we're modeling the reliability of the phone system, those two would be modeled as being in parallel. The example I gave earlier about the speaker next to your ear and this phone speaker itself, like if you put it on speaker, those might be modeled in parallel. Because if either one of them fails, you still have another path which to use the phone. Does that make sense? Right, so just drawing it back, and this is kind of an abstract comparison, right? But in the case of our electron would have two paths which to get through and get back home to complete the circuit. In this case, we have two paths which to make the phone work, and that's why those two would be modeled in parallel. Does that make sense? I saw some confusion. Does that make sense? Oh, I said parallel the first time? Oh, if I misspoke then, that's why you were looking at me funny too. Okay, let's back up just so I'm clear. I'm sorry I misspoke. So, in the case that the battery and the microphone both have to work and for the phone to work, they are modeled in series. Okay, sorry about that, guys. Thank you for bringing that up. Okay, so series is straight, right? Parallel is branched, right? Okay, fair enough. All right, so if we had the condition, all four components have to be working for for system success, this would be where everything's in series. And if we had only one component needs to work, this would be parallel. Okay? Again, apologize. Thank you guys for bringing that up. So this brings us to the concept of redundancy. So let's back up. What do we think redundancy is, Thomas? You're not sure? Elizabeth, what do you think redundancy is? Don't know? Rachel, what's redundancy? Don't know? Lynn, what's redundancy? Somebody's got to have it. Perfect. Two things that can perform the same function, right? So you might have, let's say, all right, so let's say we have a pump, right? And if that pump goes out, the town doesn't get water anymore. An engineer might say, because if the single pump fails, nobody gets water for the next 3 days, you might actually build in a second pump, right? That way you could divert the water flow if it didn't work. Or realistically, you might have like 4 or 5 pumps just to make sure that you can maintain flow. Okay? So an engineering redundancy is the duplication of critical components within a system. A parallel system, thus, indicates a fully redundant system. And a series system represents a completely non-redundant, right? Because let's think about it from a series standpoint. If anything fails, the whole system drops. In parallel, it would require all of them to drop for the system not to work. So high system reliability can thus be achieved with very low reliable components as long as we design the system properly. Right? So even if we have something that fails, say 75% of the time, if we connect enough of those in parallel with each other, we can actually get our system reliability higher. Right? And this should speak to you guys because if you guys recall in circuits, what happened to our system resistance as we continue to add more resistors on in parallel? The overall system resistance decreases, right? It's just the arithmetic, right? As we continue to add more in that 1/R standpoint, the resistance goes down. It's the same thing with our reliability, right? The reliability will go up because your probability of failure goes down. Okay? So, we're going to draw things in a system called a we're going to draw our systems in a manner known as the reliability block diagram. So before we can start to analyze these systems, it's helpful to actually draw them. And some of you have moved to the next pages already. You guys can see one there at the top. Okay? But a reliability block diagram, having a hard time saying that, is used to model the system. So in this case, what do I see on this reliability block diagram? I see component A, which is in series or parallel with B? Series. Which is then in series with what? A set of C, and these guys are redundant components, right? C is a dual redundant component, which is then in series with D. Okay, so if A fails, what happens to my system? Stops working, correct. If C fails, what happens to my system? Yeah, if one C fails, yeah, fair enough. If one of the C's fail, what happens to my system? Yeah, it keeps working, right? My system keeps working. All right, so again, just like circuits, right? A successful working system requires at least one path. So if we want to start calculating the reliability of a series system, it's exactly the same like you would expect. You just start just like you did with flipping the coins, right? All we have to do is multiply them with each other. So reliability of the whole system is R1 times R2 times R3, blah, 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 blah. Okay? And we can express that in product form like we see there. You guys should hopefully be familiar with that. It's very similar to summing, except it's very similar to like the sigma sum notation, except you just multiply it out. Okay? So due to the product rule and the fact that each component must have a reliability that is less than 1, the whole system must thus be less than every other component in that system. Right, so even if we have a bunch of 99% reliable components, the system itself has to be less than each of those components because they multiply together, right? 0.99 times 0.99 is not 0.99, it's less than 0.99, right? Make sense? All right, so most of you guys are already working on the next example, which is fantastic. So on page 53, what is the reliability of this system? All right, Jerem, what'd you get?
I got 0.7038.
0.7038. What'd everybody else get? I see nods. All right, gets a seal of approval, it looks like. Got Madison to nod, so you must be good. All right, so all we do is multiply them together, and I got 0.7038. I even rounded exactly the same. Nicely done. All right, so I'm sure you guys can already assume how this is going to go, but for the reliability of a parallel system, actually want to use the failure. Make sense? Yeah, I see you nodding and smiling. Yeah, you're all right. Good. So because what we're looking at is the failure here, we essentially become a series system of failed components, right? If you want to look at it in a different way, because each one of them would have to fail in order for it to work, right? So what happens is we can calculate the failure rate of the, or not rate, sorry, we can calculate the failure of that system by multiplying failure 1 times failure 2 times failure 3 times failure 4 times failure 5, blah, 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 blah. And then once I have the failure, what do I have to do to get the reliability? 1 minus failure. All right, very good, you guys. All right, so reliability, using the definition of the probability of failure, we actually come out to this funky looking equation, and you can write it down if you want, but the reality is you guys already know how to do it, right? It's just 1 minus failure, okay? And what that's saying is it's 1 minus the product of 1 minus r. 1 minus r being what? 1 minus r being failure, right? This one just puts it in terms of reliability, right? So reliability equals 1 minus the product of 1 minus r, right? Which is product of failure. No problem. So, but what that means here is very similar to what we were seeing again in circuits, right? Each component that we add will actually decrease system failure, which means that it does what to the reliability? Increases system reliability, okay? So increasing the number of redundant components, though, can greatly increase the cost, as you can imagine, right? If I have 100 pumps in a row, I just had to buy 100 pumps, right? If I have 2 batteries in a phone, now I have to have 2 batteries. It's going to take more. If I have 2 screens on a phone, I don't really know how that would work, but you'd have to basically buy 2 phones to get it to work, right? All right, so what you should always do from an engineering standpoint is start to weigh the benefits versus the cost. In the case of not having your town be able to have water until you can fix your pump, that's probably a pretty high cost or a pretty high impact, so it might be okay to buy a couple extra pumps, right? But in the case of your phone going out, you really need to, you'd have to buy 2 phones effectively, so probably not as big of an impact, or at least not worth the money, I'm just saying. So there's certainly an impact for sure. But all right, so page 54, and this one will take a little bit longer, but you guys know how to do the concept. What is the reliability of this system? This one is very simply the same component 3 times. All right, we about done? All right, Dustin, what'd you get? 99.9%, or what? How do we do that? 0.999? All right, let's see if I got it. So I have 1 minus R1, 1 minus R2, 1 minus R3. It's 0.9 times 0.9 times 0.9. Actually, it's 0.1 times 0.1 times 0.1, right? So I get 0.001, 1 minus 0.001 equals 0.999, or 99.9%. Very nicely done. All right, now of course, very few systems are completely redundant because, of course, we're going to not necessarily do, well, let's say we have a super expensive component that has to be its own component, but then all the cheap components we can put in parallel. So you're going to run into a complex system, no different than we saw in circuits again. So while it would of course be ideal to have everything be redundant, like we talked about, that's not always practical or cost effective. So you're going to run into systems like this, where in this case, 1 is in series with 2 and 3, 4 is on its own. So what happens if 4 fails? Still functions, sure. What happens if 2 fails? Still functions. What happens if 1 and 4 fail? Nothing works. Yes, sir. No, and actually this is just a theoretical construct. This is probably not a very, this might be like, if you were to represent this in a real system, let's say it's something that's jury-rigged, right? Where like you bought number 4 pump and then you home built something else to, I don't know. It's just a theoretical construct, right? You're right, it's not a very good real life system. But if you were to solve this system, right, let's talk about this, right? What we're going to do first is we're going to combine 2 and 3 into equivalent component 5. That make sense? Because that's going to then simplify it to this. which is 1 and 5 and 4. And then, and this is why I drew it this way, is to go through the process, right? But then we can combine 1 and 5, the new component, into 6 to get 6 and 4 in parallel. And then we can turn it into 7 to get overall system reliability. So that's overall our process. All right, so now if you go to page 55 in your book, we have a 0.9 in series with 3.9s that are all redundant. Give this one a shot. All right, so Benjamin got it super quick because he recognized that this was just an extension from the last problem. So what did you do? Right. All right, perfect. So he's going to take the last example and multiply it by 0.9. So what did you get, Benjamin? 0.8991. Is that what everybody else got? That's actually not right. Oh yeah, sorry. I stopped too early. There we go. 0.8991. It made me panic there for a second. All right. All right. So you guys notice that, before we go to talk about this, you guys will notice that there's a lot of 0.9s in reliability, right? There's actually reliability engineers actually use a term called number of nines, and that's to represent, like a 0.999 would be 3 nines. A 0.9999 would be 4 nines, right? Most of these systems are highly reliable from like a mathematical standpoint. Like a 0.9999 is a really high number, right? But if you actually start to think about that over periods of time, it actually isn't necessarily as great as you might think, right? So just be familiar that you might hear that term in reliability engineering if you go into that career, or if you're working with reliability engineers, they might say, what are the number of nines on this system, right? Or if you are perhaps in technical sales, that may come up a lot. People want to know what are the number of nines on the system because they want to know if it's only 99% effective, if it's 99.9% effective, etc. Okay. In this case, this system would be not very reliable. Right, so we already talked about redundancy, but the manner in which we connect redundancy can actually significantly, as you would expect, affect the system. So in high-level redundancy, it contains multiple systems called subsystems that are arranged in parallel. So in this case, what do we see here? What happens if component 2 on the top fails? The system still works, right, because of the bottom. Okay? But what happens if component 2 fails and on the top fails and component 5 on the bottom fails? The system still fails, right? The entire system fails. Okay, so if a single component, if in the high level redundancy where you have essentially parallel systems themselves, if one component fails, the entire subsystem will fail, but the entire whole system itself can still keep working, right? So only if multiple components fail within different subsystems will we fail. So what we see here is we have subsystem A, right, and subsystem B. And again, we require a failure within A and a failure within B for the entire system to stop working, which is, of course, highly less likely than if you were to just have those systems in parallel. Okay. However, if we were to instead connect in low-level redundancy, it might look something like this. So what we have here is essentially something that kind of looks like a daisy chain. But 1 is redundant to 1, but it's then fully connected with 2, which is redundant to 2, which is then fully connected to 3, which is redundant with 3, and so on. So only in this case, right, we have 5 component breaks here, component sets, I should say. So 5 sets of redundant components. Only in this case, if all components of the same type fail, will our system fail. So which arrangement do we believe is likely to be the better arrangement? This one? Why is that? Why is that? Yeah, you can have more failures within your system and still have your system working. Okay, very good. All right, so let's talk about the actual applications of reliable engineering. Okay, reliability engineering isn't just like, I'm not talking to you just because you're going to go be a reliability engineer. You have to think about this in everything that you do and everything that you design, and it doesn't have to be just product design. Reliability engineering in the not necessarily the engineering portion of it, but the concepts that we're talking about tonight are actually studied in business school. They're studied from a logistics standpoint, from an operations management standpoint, because you can look at multiple areas using these concepts, okay? So we use this in our manufacturing line, and later on later on the semester we're going to talk about manufacturing engineering itself. But when we're setting up a manufacturing line, we don't only have, except in very few cases, we don't only have one piece of equipment that can do the job. Because what happens if that piece of equipment breaks? My factory effectively shut down, right? So you might have 2 or 3 different tools that can do exactly the same thing, so that if one goes down, you can continue to run product. Maybe not at the full output, but at least you don't have to shut the factory down. Okay? Operations does the same thing. Let's say you are a mortgage lender company, something like that, right? Or mortgage lender, or like a title company or something like that, right? If the guy who does the stamp is out that day, you can't get the mortgage out the door. So maybe you need 2 people who can do that, or somebody who can sub in for him, right? It's a very simple concept too, right? Anybody running an office has to deal with the same type of concepts. Right? Services for sure, like utilities, you can certainly imagine that your internet company has to deal with reliability engineering, right? Switches, components fail all the time, especially when they're dealing with that many components. And in order for Elizabeth to be able to watch CSI or whatever she wants to watch at night, right, she has to be able to make sure that she has the internet to do that. And this also is for supply chain. So story time. Who remembers, you guys are old enough, you should remember the Japanese tsunami that happened 5 or 6 years ago, right? So I had a supplier, so on top of some of my equipment, so I work in the clean room, right? And on top of my equipment, I have, we call them filter fan units. So what it does, it actually cleans the air additionally from the clean room before it blows it into the tool. That way we maintain airflow in the tool so particles don't accumulate. My manufacturer for that filter fan unit was on the northern side of Japan. So when the tsunami came and that nuclear reactor went critical, my supplier was inside of the zone that was considered high radiation and had to be evacuated and shut down. I no longer had a supplier for my filter fan units. That was a failure on our company's part from having a redundant supplier. Because if I had lost a filter fan, I mean, my job actually was to qualify new filter fan units from another company very quickly, which we did and we got on board. But if I had had, in the meantime, if I'd had one of my fan units failed, I would have had to take that piece of equipment down until we solved the issue. And let's say I only own 2 pieces of equipment, now I'm running on 50% of my fleet. I'm not redundant myself anymore from a factory standpoint, right? You can see how this stuff starts building into each other. So from a supply chain standpoint, you might want to make sure that you're covered in case your single supplier has an earthquake, or maybe they go out of business, or people go on strike all the time, right? That was actually a big deal for us a couple years ago when the dock workers in Seattle went on strike. We couldn't get the boats unloaded, and I couldn't get the chemicals that I needed to my factory because there was no one to unload the boats, right? This is all real life stuff that happens, and it's not even in an engineering standpoint, right? Our supply chain failed to have multiple sources, and we suffered because of it. So if some of you do decide to not do engineering, instead go to business school, you will actually see very similar stuff to this. Okay, so reliability engineering manufacturing, we already kind of talked about. These are my little tiny tools, and you guys will get familiar later on with the Widget-Matic and the smooth widget and the widget polish. Okay, but if one of these guys goes down, let's say my polisher breaks, what happens to my factory? Factory shuts down and Andrew's out of work. Right, reliability engineering and services. Okay, so here's essentially the internet. This is how the internet works from your house, right? So we have Lynn's computer here, her user network. So she's on her laptop or her Chromebook or whatever, goes to her modem, which then goes to a bunch of box of switches, which then contacts the servers, and then the servers contact another set of servers on the World Wide Web, and that's how you dial in and you get information off Madison's computer, right, that she has on her web page. So she has her web page stored on her computer that's connected to the internet. She's on a server, you connect to her server, get the info you need, send it back to your computer. Look how many opportunities we have here for failures. If your laptop fails, obviously you're not going to go on the internet. If your modem fails, we're not going to go on the internet. But this guy, we have multiple switches, right? If one switch box goes down, we just move you over to another switch box. The internet company doesn't really care if your modem dies. The internet company doesn't really care if your laptop dies. But if you can't access their system because the switch died or their servers died, right? And let's even take it a step farther. Let's say the power company that sends them electricity for the server farm that they have out in Prineville, which is, there's one out there. Let's say that goes down. Now all of a sudden, you can't access those servers, right? So there's so many things that go into actually keeping something like the internet moving. All right, and supply chain we already talked about, right? What happens if a supplier goes out of business? That does happen. Supplier changes or end of life a product, also happens. Natural disasters, we just talked about that, and then we already talked about union go on strike, or what happens if your truckers go on strike, right? Are we going to send Benjamin down with his, Honda Prius, or wait, Toyota Prius, right? Who makes Prius? Toyota, yeah. You can send him with your Prius to load up chemical and drive it to the factory? I don't think so. All right, so do we have any questions about reliability engineering? Pretty simple and straightforward, right? All right, so you guys are all now deputized reliability engineers? All right, congratulations. Okay, so for next time, I would like you guys to turn to page 220. There are 3 practice problems there that I'd like you to look at for next time. Okay, just get the practice on them. Very straightforward stuff with what we did today. So practice problems 1, 2, and 3. All right, so our next class will be fluid mechanics. Yay, groan, whatever. All right, fluid mechanics, but that will be in 2 weeks because I'm on vacation next week, and then you guys are on vacation the week after doing your spring break, right? So that's Lynn with her tie on at Disney World. Okay, that's me in my inner tube chilling with my drink. Okay, so no class next week, no class the week after. Does anybody have any other questions before I let you out of here? Enjoy your rest of your evening. Yes, sir. Never mind, you just want to go home? All right, fair enough. All right, anybody else? All right, I'll see you guys in 2 weeks. Actually, no, I'll see you in 3 weeks, sorry. It's 3 weeks.